going to discuss Qiskit, introduction to Qiskit, and application of quantum algorithms for quantum artificial intelligence and quantum machine learning. This is the topic today. So first I will show Qiskit because most of you already may know Qiskit, or you might have some hands-on experience in Qiskit. I am seeing there are 83 members, 83 faculties and researchers are here. If I know the percentage of people who don't know Qiskit, I will go with a live demo, or else I will just continue with the demonstration. First, I will start the PPT. In the meantime, you just put a message in the chat window if you want a live demo, because live demo need 10 to 15 minutes.
Sir,
Yes,
so sorry to interrupt you. It is better to go with the live demo, sir, after giving an introduction.
okay. Then it's okay. I
Yeah,
will go.
because then yet to 160, actually, we expect 160 members to join. So yeah, they are requesting for going for the demo, sir. They're typing. I hope you could see the chat.
Yes, madam. I will go with the live demo.
Yes, sir. Sure, sir. Thank you, sir.
That's good to start with the live demo because most of us heard IBM Qiskit is the preferred quantum framework, quantum computing framework. But many members started doing self-study. Most of the members. The reason is not only money. They are not sure whether they can learn what is promised. Then there is no clarity in what we have to learn. And as all of you know, learning quantum computing is something trying to identify an elephant, 5 blind people, something similar to this one. So with that one, I will start live demo. You now starting from 1st July 2025, the link for IBM Qiskit changed to this one. HTTPS quantum, actually cloud.ibm.com. It will go to common cloud. From there we can go. But I have a direct link also. Let me share my. I have shared. Okay. Let me share my entire window. Wait a minute. I'm going to share my entire screen because earlier I shared only PPT. And feel free to stop at any point of time. I can answer your question. And okay, what is happening there? Hope you are seeing my entire screen now, right?
Yes, sir. Visible.
We go to this link, quantum dot. You note this URL, quantum.cloud.ibm/compose. Go to that link. I'm pasting that in the chat window. You should see something similar to this one in your screen. Let me paste this here in the chat window. Oh, chat is not available for me, madam. Oh, how can I share, madam? Because chat is not available for me. But sometime back, many members shared yes or no, right? Is that through Q&A?
No, sir, for us also chat is not available.
Then how can I share the links, madam? Okay, I will share here in the notepad. I will type in the notepad so you can view it and try. You have to type manually in your system.
Sir, can you share it to me, sir?
Sure, madam.
Yeah.
Just the link. Hmm, Right. This is the link, madam. Please share with your.
Yeah, sir. I will share.
Right.
Yeah, share participants.
Sorry. Okay. Now, once the screen is ready, go to Edit menu, come to Manage Register, change the number of qubit to 1, number of classical bit to 1. Change like this. I will give few seconds. Okay. After this, you will see only Q0 and C1. Now go to View menu, come to Panels, remove State Vector, again View Panel, remove Probabilities, View Panels, remove Q-sphere. Now you should see this screen. All of you are able to get it up to this stage. If anyone join through mobile phone, you can do this in mobile phone also, but it will be little bit tricky because some of the this website is not responsive. So you need to minimize the view, then do that very, uh, or else you can do it in other mobile phone by seeing here. If you have two mobile phones, I strongly recommend through laptop. Much easier, right? Okay. Okay, now what we have, the most important part in this whole screen is this right side round circle. This is called face disk info. If you want to understand
Sir,
this one, yes, madam.
sir, so
Yes,
sorry to
madam.
interrupt you. They're asking for repeating from steps, sir.
Oh, okay, right.
Ah, okay.
Step one is manage register and make this number of qubits one, number of classical bits one. This is the first step. In step, go to view menu, remove everything else except this graphical editor. When you come to view panels, you should see only graphical editor tick mark. All four should be removed. There is a tick mark, right? If you want again, you can tick mark it. You can click, then it will select it. So keep only graphical editor. Everything else removed. Is it okay? Are able to do? Right. Okay, all good. Now, the most important part is, as I was telling, this phase disk info. And the left side, what you are seeing is a operations panel. From here, you can drag and drop the gates. Before that, you have to understand what is this phase disk info. This is the phase disk info. You see here, phase disk. Right click here and view info. It will explain what is this phase disk info. The phase disk gives local state of each qubit. When I say local state, it is the live state. But the state will collapse after the measure. So before the measure only, the live state is visible. Here, it has three information. One is
Excuse me,
the
sir.
blue color. Yes, yes,
Sorry
madam.
to interrupt you, sir. I just joined now. I got this link, but the first step to proceed, can you repeat once, sir?
Okay. Go to edit menu. Come to manage
Edit menu,
register.
sir.
Edit menu. Come to manage registers. In this one, make number of qubit 1, number of classical bit 1. Then click OK. Done, madam?
Number of qubits one, sir,
Yes, madam.
and number of bits also one.
Yes. Click OK.
Okay.
After that, go to select panel, remove state vector. In your screen, the state vector will have a tick mark. Remove that. Just click, it will go.
So select panel where it is, sir.
No, madam. View. In the view menu, panels.
Okay.
In this one, remove state vector, probabilities, Q sphere, all three. And if you see code editor, that also you have to remove. Now your screen will resemble exactly the screen what I am sharing now, right? Okay.
Yeah, please proceed, sir.
Okay. The phase disk info, the color will tell the probability. What is the probability of one kit? If it is 100, it is a one kit. If it is GMT, it is a zero kit. In between, it is in superposition. And the angle, it is the quantum phase. What is the quantum phase of the system? Next one is entanglement. If it is like this, there is a 50% of entanglement. This is 75% of entanglement. If it is not entangled, there will be the black color ring will be outside. So by seeing the phase disk info of a qubit, you can understand the qubit state. Now let me put this gate, not gate. Or each gate you can't scroll down. If you click like this button, it will show your operations panel like this. So icon and then gate name. This is much easier, but after you experience, you will remember all the gates name, right? That time you can easily do this way. So um, initially you can keep panel, or else I would go with the grid because I remember all gates. You can go with this one initially. Now I'm dragging this NOT gate. The moment NOT gate is placed, you see here the probability increased to 100%, which means now this qubit is in one gate. If I delete this one, if I press delete key, it will go. Now the qubit is in 0 gate. If I put it again, it will 1 gate. Now if I put so what is NOT gate? As the name suggests, it is the NOT gate. It is also called the X gate. If you don't understand, as you know, you can right click in the operations panel, view info. That will explain the NOT gate, also known as Pauli X gate. Flips 0 gate to 1 gate. And if you want to go deeper, you can click on this Qiskit API reference. Here you can see the detailed explanation of the Xgate along with Pauli matrix 0, 1, 1, 0. And how to use, what are the other members, all those things you can get it here. So even for beginners, even this Qiskit IAP reference will be confusing for beginners. But over a period of time, you will start understanding this. Now, let me try to do this S-gate. S-gate, if I put S-gate, we expecting something, but it's not changing. Or else let me try S-gate is not changing. Okay, let us try P-gate. Nothing changing. The reason is that some of the gates are active on a superposition qubit, not on a basis state. So let me apply Hadamard gate initially. Now you see the all gates are responding. So let me put S gate. Remember earlier I put S gate, it is not responding. Now you see the S gate is rotating to pi by 2. So what is S gate here? If you click view, the S gate applies phase of I. And you remember, right, I equal to 1 into I is pi by 2, 90 degree. Pi by 2 by I equal to minus 1, minus 1 by I equal to minus I. Then again it will come to 0. So that is the complex number. I remember, I hope you remember the complex plane. In the complex plane, 0, 1, I, sorry, 0, sorry, 1, I, minus 1, minus I. 1, I, minus 1, minus I. If you remember the complex plane, you can understand the S gate will shift the phase to I. That's why we are getting pi by 2. And if you don't want pi by 2, some other rotation, what you can do? You can do P gate. So instead of S gate, if I remove the P gate and then if I place P gate, and I can edit the P gate to apply any angle pi by 4, 45 degree. Now you can see this 45 degree, or else I can go pi by 8, 22.5. So like this, I can rotate, but the P gate will work only if there is Hadamard gate. If there is no Hadamard gate, you cannot see the effect of P gate. Now I will give a few minutes for all of you to experiment some gates of your choice before jumping into 2-qubit circuit. Because this is, say, I'm not explaining how it is working, why it is working. Please note that our goal is to become fluent and familiar with the Qiskit circuit composer. Because understanding needs some mathematical concepts as a prerequisite, but this one become much easier. How to drag and drop and observe the values. So I will give you 2 to 3 minutes. Please practice yourself. If you have any question, ask me. So I will type the guidelines here. That will be helpful for you. Later I will share these notes. Okay, please do up to this point. Uh, Another 3 minutes, you have time to practice in your system. Okay, in another 1 minute, we will start 2-qubit system. One more minute.
Sir,
Yes, madam.
sir, there is an option to, it says that setup and run. After choosing the operations, you can actually, uh, for execution, you want to click the setup and run, or is there any other option for?
Only one option, setup and run only available, madam. But don't use that one because that will consume your 10 minutes allowed, because IBM gives only 10 minutes.
Okay.
And that also, if you set up and run, it will ask you for account creation. For account creation, you have to share your credit card
Yeah,
ID
I
or
tried,
something.
sir. It is not going. That's what I asked. So, is there any options to execute other than that, sir?
Madam, I will tell you the local system approach after this one, madam.
Okay, thank you, sir.
Yeah, because that is not working. Even I also not able to. I ready to register with a credit card. Still, it is not allowing me to.
Okay, sir.
Even I wrote to IBM. The problem is not solved yet. Looks like it's not only for me. It is for everyone. It is.
Sir,
Sir, sir, tell me, sir.
sir, if you want, you can use my ID, sir, for showing.
No, no, Jaikmar, not because not everyone can do that one. Let us keep this way.
No, for demonstration purpose, you can use my ID, sir.
Or else, can you share your screen and then run it?
No, better you share it, sir. Actually, I am with some other task, sir. That's fine. I'll share my credentials. You can use that
No,
one,
no,
sir.
no, 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 no need, Jaikmar. No problem. Thank Jaikmar. No need because
Okay, sir.
we need time for other execution, and then most of the faculties cannot do this way. So I'm
Okay,
going
okay,
to
sir.
tell
Okay,
simulator,
sir.
local simulator.
Okay, sir.
Okay, right. So now, okay, the 1 minute is over. Now we are going to see 2-qubit system. See, when you have single qubit, you will see some of the quantum gates are disabled, like C naught, Toffoli, swap. These are all not enabled, right? So now go to edit menu, manage register, and increase the number of qubit to number 2, number of classical bits to. Now you will have 2-qubit systems. Now what you can do, there are few gates are activated. Now if you use the swap gate, what you can see, you see here the gate values are swapped, but still there is no entanglement. So if you put this CX gate, you will see the gates are entangled. So we are not doing any operation in second qubit, but that is also getting affected because of this. And if you see Hadamard gate, you won't see anything. So CX gate will be effective only after Hadamard gate. See here, do you understand? Hadamard gate is effective on CX gate only operation. If you keep the CX gate prior to the Hadamard gate, it will not have any effect. So this understanding is very, very essential for us to experiment with quantum circuits. And this sequence also very important. Makes sense? And now, if you want to design a Bell circuit, what is a Bell circuit? A Hadamard followed by the Bell circuit. And after that, we have to add measurement. So, Bell circuit. So what we are seeing here. Okay. Anyone have any question? If not, others can mute. So this is called Bell circuit, which is the first mathematical proof of entanglement. You remember the history. The entanglement was not accepted by Einstein when Niels Bohr and other quantum physicists are proposing an approach called superposition and entanglement to study the subatomic scale physics. Um, Einstein did not accept those things. Even he argued that there are some hidden variables which are causing this kind of entanglement behavior. But after a long time, after both of both Niels Bohr and Einstein, after both of their their death. During 1964, John Bell proved mathematically this one Bell state. That's why these are called Bell state. So this Bell state tells that this system always will be in two states, meaning that if we change, say for example, I'm changing this gate, uh, not gate. So whatever I'm change, that will affect other gate also. Actually, I'm doing that after measurement. That's why this confusion is there. So when we have multiple qubits, referring to the phase disk info is very difficult. That is when you need probabilities and state vector and q-sphere. So far, so good. Can I move to next step? Any question, please ask me before jumping into the views panel. Any question? Okay, I'm assuming no question. Views, panel, and state vector. If you see the state vector, the Hadamard, this well state is showing 0 state only. And if you see the probabilities, it will show probability for 2 states. Remember, 2 qubits can have 4 states, right? But because of the C naught entanglement, only 2 states are active. Other 2 states, they are not getting any values. That is the purpose of entanglement. And if you see the Q sphere, panel Q sphere, you will see the same thing in a visual Q sphere approach. So state vector, if you want to understand what is the state vector probabilities mean, you can click here and then read it. Yes, the state vector simulation completely characterize the final output state of the qubit. And probability is a histogram of uh, because very small, that's why you opened this one. The state vector, the 5 qubit limit, state vector is visualize the quantum amplitude as the bar chart. So that is what the state vector. Probability is the probability of the states. So state vector will give you the final state. The probability will give you what are the probabilities for other states. So with reference to the circuit what we have designed, it may be difficult to understand for beginners. So I have to explain with the fundamental concept. Shall I go with that fundamental concept? So remember this one. This is what the Bell circuit. I recommend all of you take a screenshot from your screen. This circuit alone. Take a screenshot. Now I'm going to delete everything and okay. Let me remove everything. See, now I'm going to demonstrate with the help of this visualization. Now you see, we have the amplitude is 100 or 1 full amplitude for 0 state and probability also 100 percentage. The Q sphere shows here. If I add Hadamard gate here, it will flip the LSB, least significant qubit, which will go to two possible states. That's why you see 0001. So 2 states. This one, this one. So if I add Hadamard gate with the other one, the first qubit also will become 00. So now we have equal probability and equal amplitude. And all possible states are having equal probabilities in the Q sphere. You can see here. So if you come over here, it will show the state also. You see phase angle 0 for 25%. For phase angle all are phase angle 0 only. But if you want to display the now you will see phase angle in the different color also. It is displaying phase angle also. Now if I apply a phase angle to this one for 0, 1, you see here these two qubits are become 92. So now you can play around with the different phase angle also. So now you are getting some idea, right? So playing around with the qubit states and seeing them how they are reacting to your qubits. It is a good way to understand by randomly playing around. Still, you are getting the grip on quantum circuits. Any question here? I'm expecting few questions. Please feel free to ask me the question. I think we are not in rush. The goal is we have to understand something. So even though I have a PPT, prepared PPT, don't worry about that one. I will focus on this one. Make sure that you are understanding how to use circuit composer. Any question? The chat window is not enabled. Otherwise, I know you would have asked me. Okay. If no more question, let us move on to 3 qubit. You will see 3 qubit also same, right? But you will understand more about the way how this qubit are
Sir, there
changing.
is a question in the chat.
Chat enabled, madam.
Sir, actually, for few participants, it has been enabled, sir.
But I am not seeing that. It's not enabled for me.
Okay. Does the color code indicate something? They're asking.
Can you paste the question in my chat in my WhatsApp,
Yes.
madam? Or else this is my WhatsApp number. If you have your question, you can directly ping me. This is my WhatsApp number. You can connect with me in LinkedIn also. You can directly ask question to my WhatsApp also. I will keep my WhatsApp active. What is the question, madam? Can you read the question?
Does the color code indicate something?
The color code is the phase angle. The phase of the circuit, the qubit. For example, uh, if it is blue, it is a 0. If it is pink, it is 90 degree. If it is red, 5 degree, 180 degree. If it is yellow, 3 pi over 270. Sorry, what is it? 270 degree. So that is the color coding. For example, if I make this as the see 2 pi instead of pi by 2, I'm making this as the 2 into pi. You will see the color become different color. Or if I just put pi, you will see it is in the red color because now it is pi degree. So the color coding indicates the phase angle called the phase. We can control by placing the necessary gates and making the changes. There is one more gate called U gate. We can supply all 3 parameters. Now let me add Hadamard gate to third qubit. Now you will see all 8 states are having equal amplitude and equal probability. And the U gate, it allow me to update the 3 parameters. So I can do pi by 2, pi by 4, and pi by 8. Now you will see the you will see entirely a different values for different parameters by changing the parameters. So how changing these parameters affecting? Because the U gate, let me show you the U gate view info. The U gate, um, the U gate matrix is cos theta over 2 minus e power I lambda sin theta over 2 e power phi sin theta over 2 e power I times I phi plus lambda cos theta over 2. This is the formula behind this behavior. Because of this operation on the qubit 2, which is 1 over root 2 1 over minus 1, that is the state of this one. So when I multiply that one, which will affect others also. Now if I try to put an entanglement to second and third, you will see it is affecting others, but it is reducing the probability for irrelevant qubit. For example, the first qubit is not important now because second qubit and third qubit are entangled, or whatever happening in the first qubit, that is uh, irrelevant of these two qubits, meaning that that won't affect their state. For example, even if I put t here, it will affect only the first qubit. That will not affect second and third. But if I entangle the first and third, for example, if I want to entangle like this first and third, you have to select this, go to edit and target qubit 2. So if I entangle like this, you see it is purely affecting third qubit. Does it make sense? It may not make sense initially if you are attending very few FDPs now, meaning that if maybe for many it may be the first FDP. For few of you, it may be fifth or less than 10. It may be connect the dots. But in my humble opinion, you should attend at least 20 FDPs on quantum technology to understand this one. Unless you are full-time learner. So if you want to see one by one, select the inspect, then click one by one, then you can see all the Hadamard gate. See, when I apply Hadamard gate, all are in the same state. You see here, all are 12.5% like this. Then next step, applying T gate and U gate to the first qubit and second qubit. That is affecting only the second and see the first zero, the third qubit is not affected. And next you are entangling. After the entanglement and then P gate, you are getting, actually after that there is no much difference. But the moment you put measurement operator here, so you stop inspect, then if you put the measurement operator, everything will collapse. So something very important happening during the measurement operation, which is called collapsing to basis state. Whenever you are measuring your quantum state, that measurement operator will collapse. So the final result is 010 is your final result for this operation. So we did something and then the output came 010 is our output. And is this any meaningful circuit? No, this is a random circuit. I on the spot designed such that I want to explain each concepts, like multi-qubit gates, how to drag and drop, how to edit, how to visualize the output, and all those things. Now I can use this barrier like this, put a barrier here, here, activate all qubits such that they are in this way. So if major operation, you can apply the barrier here like this. That will give you more cleaner circuit design. And if you want to initialize, you can, for example, this circuit I want to initialize, you can put a 0 gate, then that will become 0. Now you see different output you are getting. So if you want, you can reset. Like this, many other operations are here. If is classical operation, conditional operation. If you put an if statement here, usually it should followed after for this gate to happen, we can make it that the classical register is 1, then only you have to do this operation, something like that. It's a classical operation connected to quantum data. But using the if logic inside your quantum circuit is not recommended unless there is no other way, because that will increase the ancillary qubit count internally. Any question? Anyone send the question to me in WhatsApp? Let me check. No, no one asked the question in WhatsApp. If there is no other question, I will continue to the execution part. So IBM is charging $98 per minute, and it is not, see, compute resources, right? If you see here, these are all my resources, and IBM Pittsburgh 156 qubit, 127 qubits. These are all processor types. It's going to run all those systems, but whatever it is, IBM is going to charge $98 per minute, and you need to get access to that one. And of course you will gain access because it is a research project. Some funding agency is going to fund your research, so you are going to get it. But it is not, it is recommended to run this circuit in a simulator in your local system. That one, if you have a 16 GB RAM and Windows or Linux laptop, you can do it on your screen, on your laptop. Or else the easy way is Google Colab. I'm not strong recommender to Google Colab, but considering the audience, the strength of audience here, I recommend all of you go to Google Colab now. Let me start my screen, Google Colab. Collab.google. I believe all of you know how to use Google Colab. That's the reason I selected that one. Go to Google Colab. You do along with me. Select new notebook. I'll give some time. Select new notebook. Inside the new notebook, do this one. Exclamation. Pip install. Skit space. Skit -aer space. Add plot lib space file latex enc. You need to install these 4 packages: Qiskit, Qiskit AR, Matplotlib, and PyLatex ELC. Hope all of you are able to see this one. I am going to shift enter and it will take some time. All of you do this one in your Google Colab. After this one, what you have to do, I think it complete everything. You have to go to runtime, restart session. This is necessary. Otherwise, the PyLatex ENC will cause issue later. So do runtime restart session. So what you have to do now, I will type here. First one is Google Colab. Second one is new notebook. First step is pip install. Next step is runtime restart session. Okay, this is what you have to do now. Later I will share this notes. No? Now I can click this one and then hide it. Okay. Now what you have to do, you are going to do what I am doing here. So the screen is visible for all of you. You are equal to, sorry, after pip install, some skip port quantum register, comma classical register, comma quantum circuit. These 3 things. Next step, QR equal to quantum register of 3. 3 is the 3 qubit. CR equal to classical register of 3 classical bits. UC equal to quantum circuit equal to quantum circuit of QR comma CR. Now QC dot H for Hadamard gate. QR 0. Now QC dot draw QML. Okay, let me run this. The error it is doing. Did they make any mistake? Sorry. MPL. My bad. It is MPL, Matplotlib. It is MPL, so not QML. So what you are seeing here, Hadamard gate applied to 0th qubit. Now if I apply QC dot H of QR1, you will see Hadamard gate applied to 2nd qubit. And similarly, I can do QC dot H for QR2. But if there are 20 qubits, will you do like this? So you can apply one line QC dot H. This will draw or this will apply Hadamard gate to all 3 qubits. Then what is the next qubit operation we have to do? T gate for Q0, right? So T gate for Q0. QC dot T for QR of 0. Now you see T gate is applied. The next one is U gate for second qubit. Right? U gate for second qubit. Now I'm going to face problem because I don't remember the syntax for U gate. QC dot U. I have to give 3.14 over 2, 3.14 over 4, 3.14 over 8. I think it should work. Yeah. Okay. There is one syntax is missing. Maybe for U gate, which gate? U gate missing. Yeah, maybe I have to pass the qubit count. The qubit, which qubit it has to? Yeah, QR. Sorry, 1. Yes, it is fine now. So sometimes it will happen. You will design the circuit easily in quantum circuit composer, but you don't know the code. That is where the view panel code editor helps. If you activate the view panel code editor, you will see the code. If it is in open COSM, change it to Qiskit. Then it will show the code. Here you see the you get P. See pi import numpy from numpy import pi. So they are used pi value. I hard coded, they imported. You see, that is how it works. Indeed, if you are good at circuit composer, you will get the whole code from this code window. That is the reason why initially I suggested you to stop all those things. Otherwise, you will pay attention to the code. You will not pay attention to the circuit. That's why I made like this. Hope you understood the purpose. That is easy way, but easy way will not help you to learn. Hard way will help you to learn because you have to teach, right? So if student asks a question, you should be able to answer why it is happening or what is the reason. That's why I made you to learn a circuit design, visualization of phase risk info, understand the behavior. When it is necessary, we are seeing. So now you have everything here. Now we have to execute the circuit. To execute the circuit, we need a simulator. The simulator is coming from Qiskit -AER import AER simulator. Yeah, it came everything. Sim equal to AER simulator, job equal to sim dot run PC QC, job result dot get counts. You will see the get counts. It is giving the count also. The output we got, but the output we want to visualize the probabilities. Um, Qiskit visualization, import plot histogram, plot plot histogram counts. Now it will draw the histogram. You cannot compare this output with this output because this one is live execution simulator, but that one is in the after the measure. So it is like the final output what you are seeing here. And we are seeing the probabilities for 0, 1, 0, or the higher probability for 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 1, 1. Okay. Now, what demonstrated, even without referring anything, we can type our Qiskit program. We don't control C, control V. And I request all of you to come out of that difficulties. Quantum programs are very difficult. We need to get a sample, control C, control V. After that only we can make our change. You have to come out of that thought process. Normal classical program, how you are doing, you have to follow that approach. And I'm assuming all of you are good at Python. If you are not good at Python, it is a right time to learn Python from um, a professional industry trainer. If you cannot spend that much of time, you can learn from W3 school. W3 school is the beginner level one, but that is a good starting point. Then go to Geeks for Geeks. These are all good sources, and then there are many Udemy courses also. So you can go uh, learn from that free sources also. But my strong recommendation is that find a mentor who can handhold you and guide you in the right direction. Where is the notepad? Okay, any question? I'm ready to answer a question before moving on to the next topic.
Participants, if you have any questions, please ask.
Python learning, W3 school, followed by Geek for Geeks. Okay, if no more question, let me continue the other aspects of uh, the quantum programming. Here, if you want to visualize the Bloch sphere or Q sphere, you cannot visualize after measurement. So you need something called from skit from skit dot bottom import state vector. So before measurement, you assign state vector of your circuit, state vector of QC. Now from skit, sorry, skit dot visualization import plot state Q sphere and plot state Q sphere of SV1. This will draw the Q sphere. Oh, sorry, I have not executed from the beginning. Let me execute. Execute. Is that I have to here. Execute, 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 execute. 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 Now you will see the Q sphere here. So the Q sphere shows those 5 states which have the higher probabilities. Make sense? Like this, you can visualize them using the array latex also. There is a Qiskit visualization called array to latex. If we use array to latex, it will give you the state vector. Let me do this here. It visualization array to latex. Array to latex of SV1. You will see a state vector of 8 value. You see there is 8 and it is coming in this direction. I can change the direction also. Get the syntax. Precision, prefix, string, integer, source, boolean, precision, integer, max size. No, direction changing is not feasible here. But you can see here now the values are complex numbers. There are 8 values. Any question here? Because next we are going to see density matrix. Before that, any question, please let me know. Checking my WhatsApp also. There is no question. Okay, no question. Great. Now, there is something called a density matrix, which will give you a more uh, granular detail or the deeper information for which you have to, that is also available in quantum info. You have to import density matrix like this. And density matrix also collected before measurement. PM1 equal to density matrix gives it, right? Now, I am going to display array to latex PM1. Now you will see 8 by 8 matrix. 8 by 8, 8 by 8 matrix. If you want to play around with this one and then understand how these states are dynamically changing, you can play around. But one of my mentor, who is a doctor in PhD mathematics, he told KG, don't worry about this mixed states, density matrix, intermediate states. Focus only on the logic. After the output, how are you going to use it? And when designing the mathematical model, a high level idea how these states are mathematically changing. Focus on that one. But obviously, to go to that level, you need a strong foundation in mathematics for quantum mechanics, which uh, needs some more focused efforts. If you are looking for specific subjects or you want to go deeper into mathematics for quantum mechanics, please contact with me. I will connect with you, Jaikumar. Jaikumar is the person who can teach those concepts. Okay, correct. Any question? If no more question, we will stop here. because I know there's a overwhelming of information. I'm also not feeling well, so not energetic as usual my session. So some of you might have attended my session already. You can find the difference because I have a severe throat. Fever. Yeah. Madam, when should we start the next session, madam? We'll 5 minutes break. How long, madam?
Sir, yeah, sir. 7:30 next session. 5 minutes
Okay.
break you can take, sir.
Yeah. Please take 5 minutes break. After that, we will start. And feel free to ask the question, send the question to madam or me, and we will start that one. Okay.
Okay, sir.
Thank
Okay, sir.
you. Thank you.
Dear participants, kindly fill in the Google form for the session 3. Next session will be starting by 7:30.
Ma'am, this is a session phone now. Ma'am.
Sir, the current session is 3. The previous session was 3. Upcoming session is 4. Sir, can you hear me? Inaugural session is not included, sir. Divakar, sir, you were asking me, right?
Okay. No. Just sir says now that last session will we take first, and after that I will take first session. So that's why
No,
I'm asking.
that is fine. The topic is changed because he's the same resource person. So is it not an issue, sir?
Okay, ma'am.
Fine, sir.
Excuse me, Prabhadevi madam.
Yes, sir. Yes, ma'am.
Ma'am, this form, we are not able to access it, no, madam.
This Google form, ma'am.
Yeah, Google form.
Yeah, it is with everyone only, ma'am. You can access. Link is not accessible or
No, we are not able to go to the new tab itself through this. And that is
okay.
not getting copied also.
Wait, ma'am. Wait, ma'am. I'll share one more link. Please check the one that I sent now, ma'am.
1 second, madam.
The WhatsApp group I have shared.
WhatsApp, 1 second.
Actually, it is opening only.
Yeah, through WhatsApp I was able to access, madam. Thank you.
Fine, ma'am. Yeah, ma'am.
Can you start now?
Yes, sir. We can start.
Okay, right. So considering the last session was kind of demo or kind of hands-on, let me cover up what are the things I planned for this Qiskit and algorithms for quantum AI. Um, to put it into slideshow view. So what I have planned is, this is what covered already. This PPT will be shared with the organizers. Later they will share with you. First thing, what you have to understand, quantum encoding. So before jumping into quantum machine learning or quantum optimization or any quantum operation, we have to decide what kind of encoding we are going to do. So it can be basis encoding or phase encoding or amplitude encoding or hybrid encoding. But I use the word density matrix. This is uh, my preference to use density matrix, but you can understand this as a hybrid. For my easy understanding and the underlying technique, I am using this one. So here you can see the whatever number we are using, that we return as the, for example, if you want to encode number 4, the binary value 0, 0, qubit for 4 bit 0 1 0 0, right? This is number 4 in the classical world. So correspondingly with the 4 qubit, we the 0 0 your basis encoding. So in basis encoding, we will use the um the number of qubits and number of bits will be equal, and we will use the basis states to represent the number, classical number, what we want to encode into quantum system. And this cannot handle large data set. Of course, fundamental operation will be useful. Next one is the phase. If you remember, there is a one more formula for psyket superposition, alpha 0 ket plus beta e power iota theta 1 ket. And with e power iota theta, the theta, you see here, this theta can be used to decode our number. How, for example, if I want to decode 4, how I can decode 2 theta? So, place this into radians. 0 radian to 2 pi radian. Because normalization operation is very common, and I believe all of you know this one. So, you are able to normalize this 4 to 0 between 0 to 2 pi. That theta can be applied here using U gate or P gate. And next one is amplitude encoding. Here we are adding this 4 as a probability amplitude to X. ICAT will be remaining same. But see, for example, if you have 4 qubits, you have 16 states, right? Starting 0, 0, 2, 1. What we have to do, we have to increase the probability of the state what we want to update. For example, we want to update the number 4. Number 4 falls under 0, 1, 0, 0. If you put, the probability will be 100 over 16 because there are 16, which will result in maybe 6.75. Instead of equally assigning 6.75 percentage for all, you assign all 100 percentage to 0, 1, 0, 0 state. Other states will be 0. That is through the probability xi. That is what amplitude encoding. But amplitude encoding will use less qubits compared to basis or phase encoding. Density matrix is something very advanced. You can initialize your all qubits at once using this density matrix encoding. Not all quantum frameworks can support this hybrid approach. It is applying or multiplying the probability with the outer product of your states. So outer product of your states will result in a density matrix, and multiplying with the probability will give you the new state what you want to encode. And this encoding is essential part for any operations. Any question in this slide? Okay, if not, we have to understand the VQC and PQC when you are building the solution. I will go back to my circuit. The circuit what I built using the IBM, sorry, the Google Colab. That is the Google Colab. This Google Colab, whatever I built, it is using purely purely quantum approach, right? So this quantum circuit performing some operation, returning some value. This is a simple quantum circuit. It is not having any parameters, but it having any parameter. But what I did, I hard coded that parameter here. You see here, I hard coded this one. But if you want to convert this as a PQC, meaning the parameter is quantum circuit, either U gate or P gate or any gate which accept parameters. That is the important thing. The H no parameter, not no parameter, CX no parameter, I P no parameter. How I'm telling you, if you click here, you see here there is no for parameter, it will show the parameter here. So only few gates have parameter. Rx must have parameter. All rotational X, Y, those things have. You see, these are all parameter, the gate, parameter gate. If you are using this parameter gate in your circuit, that circuit is called PQC, parameterized quantum circuit. Is it good? Do you understand now? So this circuit is a parameterized quantum circuit. This circuit will be part of our whole solution. It is not the solution. It is part of solution. The quantum part is part of solution. You see here, data encoding, what we have seen now. After encoding, we are passing the encoded data to a quantum circuit, which is called a PQC, parameterized quantum circuit. It will perform some operation. The operations will be measured. The measurement will result in a classical output. The classical output will be analyzed using a classical loss function or cost function. Those who are from machine learning background, they know what is loss function or cost function. After the loss or cost function, that will be fed to a classical optimizer like ADAM, Probila, SGA. There are many optimizers. That optimizer will optimize the parameter again, the theta value again, that fed to the same circuit. Then that will generate output. So it will be repeated till the output of current iteration converge with the previous iteration with the given error epsilon. So either the number of times we wanted or the convergence reached. Within this time, this circuit will be repeated. That is the whole circuit is called VQC, variational quantum circuit. In the world of quantum, if you see the word variational, that indicates it is a hybrid circuit, meaning that there will be a PQC and a classical loss and optimizer. Any question in this slide? Checking my WhatsApp message if there is any message. No message.
There is a question. Sir, his basic encoding is applied for general problems.
No, basic is applied for fundamental operations, not general operations, because some of the general operations need amplitude encoding. Even phase encoding is not sufficient. So when it's coming to encoding, you should learn all four encoding. You cannot learn one encoding and proceed with one encoding method. Sorry. When the approach is, for example, you are running a circuit on IBM QPU and you want to repeat the same circuit in D-Wave, you cannot use the same encoding. The algorithm may look similar, but the encoding has to change because IBM is using a gate-based method and D-Wave is using annealing. That is one major difference, annealing or gate-based. Even within gate-based, you cannot assume that all gate-based systems are compatible. For example, the native gates available in superconducting may not be available in neutral atom. So you have to consider these native gate compatibility and what are the algorithms you can build and what is the best method to do that one. Based on those things, you have to design what encoding system is suitable for your problem statement. So we cannot take basis encoding alone. If that is the case, of course, there are many circuit I have seen at the beginner level. They used basis encoding for all operations, so it will work. It will work. Certainly, it will work. The cost is double because if you use amplitude encoding, you can reduce n qubit to n by 2 qubit. You understood, right? That's why I'm telling you better learn data encoding. Don't go with basis encoding, even though it is recommended for beginners. You may think I am a beginner, I want to do basis encoding. If that is the case, please proceed with the basis encoding for the initial 1 or 2 programs, but later switch to what is the correct encoding for your problem statement. If you want to learn the correct encoding, you read a book by Maria Schuld. Maria Schuld wrote a book, Supervised Machine Learning Using Quantum Computing. That is a good book. I think chapter 7 and chapter 9, they covered this encoding. Will show the book. I think it is there in this slide also. I will show.
Sir,
This,
this encoding is just like the transformer encoding. Is it like that?
No,
it's different. Okay.
See, transformer encoding within our classical world, it is like word to vector, and see in one domain to another domain, right? In classical world, if you use encoding for transformer, the transformer need the vector in the specific format such that it can use the weight or bias or any other matrices with the input vector. That is why we are going for the encoding in the classical machine learning. But in quantum machine learning, it is basic requirement. Without that, you cannot proceed to next step. So that answer your question.
Yes, I understood.
Yeah, great. So this is the book I recommend. There is one more book, Unsupervised Learning also. Both books are good book. You can read from this book. You can read that encoding. In my opinion, that is a good book. And these are all the books for mathematics. Let me go back to our concept. So this is the variational circuit. And yeah, there are many algorithms in quantum A and quantum machine learning. Here, I would like to tell you few points about my personal journey because that will help you. I am a software engineer, worked in almost all computer languages, started from COBOL programming. So in 1996 and all, I started my career, and COBOL, FoxPro, Oracle, like that I moved. And 2008, I came to a language called R. That is when I got introduction to data science. Then I became a data scientist. I worked in Dell as a data scientist for 10 years. So when I started quantum computing 2004, I don't know which path I can choose. But fortunately, the data science career helped me to jump into quantum machine learning. Now you understood what is my career path in quantum, right? Even though I have not studied quantum as a part of academic, of course, I did my master's project in 2010 on quantum computing, but quantum computing or quantum mechanics was not part of my academic syllabus, any of my academic syllabus. So my job at Dell helped me to become expert in machine learning. From there, I logically switched to quantum machine learning. So that is my quantum machine learning journey. So for those who are attending the session from software engineering or machine learning or any other computer related career or computer related skill set, you can target QML as the entry point. Those who are from physics, mathematics, you can plan the research part where you are analyzing the behavior and build the mathematical model. Those from core, right, mechanical, civil, electrical, electronics, or finance, you can plan the domain expert, subject matter expert. So, any question? Someone is asking question. No question, right? Okay, right. No question. Okay, right. So the QML is it is easy to enter into quantum career through QML algorithm. You can see here almost quantum all machine learning algorithms have their quantum counterpart. So supervised learning, you have QSVM, QNN, QKN. Indeed, my first experiment was QSVM only. Then unsupervised learning, we have QPCA, QBeams, and quantum inspired algorithm, tensor network, quantum inspired annealing, quantum inspired neural network. There are some fundamental algorithms, the growth search. This can be used for quantum machine learning also, because I have seen few algorithms based on quantum search in quantum machine learning and HHL. These HHL still needs a fault tolerant system, but still it can be used as a POC. Any question in this one? Okay, if no more question, I expect few questions from this slide because this is one of the familiar topic for most of the attendees. Only thing I added the word Q in front of that one. Okay, right, cool. No more question. Let us move on to the ending part of the first session. Actually, this is the ending part of the first session. I recommend watch this Veritasium video to understand why we use complex number for quantum, and 3 blue 1 brown is not for quantum but for mathematics, and Gilbert Strang all of you know. Then this is for QML and then quantum artificial intelligence. And I recommend the movie Transcendence, which is a movie on, it is not here. Okay, there is a movie called Transcendence. This is the movie, 2014 movie by Johnny Depp. What this movie? They are talking about. It is a science fiction talking about quantum and artificial intelligence. Quantum artificial intelligence and photonic quantum computing is main part of this movie. I strongly recommend uh, watch this movie because many people, when the word quantum comes, they will talk about what is this movie? Avenger movie, right? Avenger movie Endgame. There is a quantum realm and all. Even Ant-Man. Instead of those movies, this is the good movie which is exactly dealing with quantum and quantum AI. Okay, that's all for the first session. Next session, let me start the next session. Any question while I am starting the next session? I'll wait for Q&A. Next session, I will complete the PPT. After that, I will start the demonstration. That time you will be able to ask more relevant questions. Madam, can I start the next session? Any question? Okay, right. Let me stop this session. Okay, stop. Okay. Now I will tell you one story. Not story, it is a real incident. Sometime back, I was traveling from Bangalore to Goa to take a quantum session. Not Goa means don't think that I went for vacation. It is a quantum session I delivered. While returning, a curious person who is sitting next to me asked the question, "What are you doing?" I told quantum research. He asked the detail. Then later he asked the question. That is good, exciting, but what are you doing for your living? Do you understand? Even 3 years earlier, 3 years ago, quantum computing was not considered as a job which will give you uh, or which you earn money. That was the fate of this quantum computing domain. There were jobs for researchers, but normal undergrad or normal people cannot find jobs in quantum world. There is a real reason because this industry is in the nascent stage and it needs researchers who will help to build hardware, control system, necessary software. And that is the demand was there at the time. Now only, even if you recall, when Qiskit um, released, Qiskit was there in IBM a long time, but they released to public in 2017 only. 16 they released, but made it official in 2017 only. And many companies even now don't release their versions for public access. So that is the status of quantum computing now. But industry needs solution yesterday. And quantum computing is telling, if you see the feature of this generation, feature of quantum computing, we are in the first generation. And right, first generation tech professionals. It is like a student who joined a first batch of the new college. Everything is not defined. Everything is theoretical. Everything is simulated. Starting from classroom to laboratories. Everything. That is like we are in the first generation. We are having only simulators. We cannot afford real QPUs. That is going to happen till 2028. Then 2028 to 39, second generation, where something real will happen. We will find more jobs. That's why I used to tell my mentees, are you ready to work hard till 2028? Most of the students will stop there. Okay, G, then quantum computing is not suitable for us. Yeah, I understand your situation. Better pursue some classical skill set and then find a job. Because quantum is the first generation itself will end in 2028. After that only we will find a good jobs. Till that time, you need to build a strong network and research popularity and a strong network to find a job. Second generation 2028 to 39. Third generation, you see there is a overlap. 2031 to 2039. So 2030, 32 and all, you will see a tremendous demand for quantum computing. One good thing for those joining the FDP, the academy will start teaching quantum computing long time back. And academicians can find jobs now itself. That is why we have a special course for academicians, 5 days in-person course at Bangalore. Those who are interested, you can contact me. So this tells us that there is a great future for quantum computing, but not now, starting from 2028. Now, okay, I agreed. What is the future? But you are telling no quantum computer now, because this is the list of quantum computer. You see here, as of now, available quantum computer, IBM 1021 qubit, and atom computing 1180, but this is a neutral atom, and quantum annealer 5000K, but this is a quantum annealer. So quantum computing is not ready to build production ready. That is where these quantum inspired solutions come into picture. So there are multiple platforms, but I can recommend these three platforms. One is Toshiba, other one is Fujitsu, third one is Microsoft um, um, OQC, Microsoft Optimizer. Yeah, QIO, Microsoft Quantum Inspired Optimizer. Yeah, this one is Azure Quantum QIO, SQBM from Toshiba, uh, and Fujitsu is not available in Azure, but you can find it out in their website, Digital Annealer. Please note down these three things: Microsoft QIO, Toshiba SQBM, and Fujitsu Digital Annealer. These are the three quantum inspired platforms which are used to build quantum solutions today. Why? Because these are all classical systems, classical HPC systems running quantum algorithm. Now you have a question. How come quantum algorithm run on a classical system? If that is possible, then why have to spend 15 million to 40 million dollar to build a quantum computer? Right? Anyone having that question? No question? Okay. Okay. If you don't, I think you know why we need HPC. I will move on to the next slide. So the key components of quantum inspired algorithm is there will be a problem definition layer and algorithmic layer and execution layer, hardware layer. It is common to all solution, right? Any solution, there will be problem definition, there is an algorithm, then execution, hardware layer. But what is special with the quantum inspired? Here, the algorithm is quantum inspired techniques. In normal quantum computer, it is a quantum algorithm. So what is the quantum inspired and quantum? That is the difference you want to understand. Quantum inspired versus quantum versus classical. So we have to understand what is the main, okay, my bad. What are the main differences between these three techniques? I know they are look like something similar, and these four layers are common to all. But what is the main difference? In classical, remember just now when madam asked the question whether we can use the basic encoding, and then follow-up question, is it similar to encoding in your classical models, right? So like that kind of doubts will come when you see or when you go deeper into these three algorithms. But the major difference is that in classical it is Boolean algebra with binary number. In quantum, it is linear algebra with complex numbers. In quantum inspired, linear, sorry, linear algebra with complex number minus interference or any other interference is okay. Entanglement also we can do minus interference. That is what quantum inspired. See, some of the operations only quantum hardware can do. See, now you are seeing this screen, right? I will show that. See, you are seeing now it is executing, and you are seeing my Google Colab. Here also it is executing and then showing result. What is the meaning? Whether IBM is keeping a quantum hardware there in their server. No, this is running on classical system. So already it is proven. We can build a classical simulator to run your quantum algorithm. But the quantum inspired algorithm, we cannot include interference. We can include superposition and entanglement. So the interference related operations need to be reformulated as a separate or different mathematical operation which is suitable for classical hardware. This is one thing very interesting to know. And anyone heard what is quantum supremacy? You might have heard the word quantum supremacy. If you don't know, let me know. I will explain. Okay. So if you can connect quantum supremacy with this concept, then you can understand clearly. Any questions so far? All good? Because now I'm going to enter into the deeper concepts. These things, they will need some prerequisites, meaning that at least you should have experienced one quantum algorithm in action, or at least once you tried one small quantum program on your own. Then only most of the concept what I'm going to explain now you can understand. But you have never done that one. In that case, KG, what I can do, that is nothing wrong in it. Learn this one now, later apply in your quantum journey. Because in quantum journey, those who are into this building the solution for client, they only come across quantum inspired algorithms because we want to make money immediately, right? Remember the person who asked me, what are you doing for living? I cannot tell him because my client never told that you should not reveal that you are working for me. So we are working on mission critical research. That is where we are getting money. So then when you are going to into that level only, you will come across this quantum inspired algorithm. Because we need a solution, but we cannot have quantum system now. There is also other limitations also like security, and there are some facilities which is not connected to internet at all. There are many facilities, secret facilities, in every country they have. So those systems cannot connect to quantum computer unless they have the quantum computer inside their data center. You understood the problem, right? Those kind of situations, we have to go with quantum inspired algorithm only. Then these are the things: parallelism, entanglement, and tunneling. But no interference is involved in this one. And these things are used in AI, cryptography, and logistics. So limited functionality only we can build. We cannot use QIA for all problems. And these 4 layers: problem definition, algorithm, execution, and hardware. So here you can see here root optimization. For example, root optimization problem, quantum inspired neural network, and CPU, GPU, and all. So these are the various industries: logistics, supply chain, finance, and optimization. These are the various problems which can be used to build quantum inspired solutions. I'm working on this one, finance, stock portfolio balancing. That is what my area, where I'm building a solution for one of my client. And I'm working on other things also. At least this one only I can share this much. Any question here and in these 3 slides? That is already 8:10. And this is third day, right, madam? Third day of the session, right?
The second day, sir.
Okay, second day.
Yeah.
Any workshop or practical session happened yesterday?
No, sir.
All introduction only.
Yes, sir. Introduction.
They cover the applications of quantum computing. Right? Why we need quantum computer?
No, sir. He covered the mathematical parts. He covered the last applications. Not it fully covered.
Okay, in that case, since there are no question in this slide also, I will go back to application. That is in this slide only. I assumed that they know application. That's why I came here. You see, these things are all I did not spend my
Please
time
proceed
because
that.
this is also in the same slide. You can see here, quantum computers are used to solve NP hard problems. And there are class of problem based on the computing complexity NP hard, which are usually exponential or factorial complexity. You can see here these two curve, the pink and purple. Others are classical system can solve. These are all for classical, right? But this one is for quantum. Why? Because quantum can operate natively parallel. When I say natively parallel, you may not be able to understand why it is natively parallel. But the mathematical part, what was covered yesterday, will help you to realize that the states are having probability. That is where the native parallelism comes into quantum computing. One thing you might have wondered, I don't know how many or what is how many number of FTPs you have attended related to quantum computing. One thing, the annoying thing repeatedly told, learn mathematics, linear algebra. For many people, it is annoying because I am conducting in-person session, right? During the in-person session, the moment I was talking about the mathematics, I will see a dissatisfaction or some uncomfortable feeling in the face of almost all attendees. So I know it is it is not very pleasant experience to enter into mathematics now because we escaped or completed our degrees and then jumped into job now, doing our job. Now again we have to go back to basics. It is very difficult. But for first generation uh, quantum computing professionals, mathematics is essential. Maybe second generation, they don't need mathematics. And some of my mentees told KG, why then I want to go back to classical. I will jump to quantum career in the second generation, which is 2031. Yeah, there are another 6 years now, right? Within 6 years, there will be a lot of people. When you come 2031, it will be very crowded. That time, what you have to learn, it will be much more than what you are learning now. You understand the justification what I'm telling? The only difficult part is mathematics. And the computing complexity clearly tells that it is a mathematical problem. So one general guidelines is, if you see a problem of uh, higher order ordinary differential equation, higher order partial differential equation, or combinatorial problems, those are all suitable for quantum computing. That is what you have to remember. I'm typing here. Problems suitable for quantum computing. Higher order ordinary differential equation, higher order partial differential equation, combinatorial problems. So these are all the use cases which are suitable for quantum computing. Now you will have a follow-up question. Okay, how can I identify higher order differential equation? Obviously, if you are from computer science background, you cannot find. That's the reason why, remember in the previous slide, I was talking about this one. Domain, physics, mathematics, then computer programming. So the domain expert or subject matter expert in the domain, they will tell the problem. They will identify this problem is a higher order differential equation problem. Then they will explain the problem to a physics person. That physics researcher will try to connect that one with the quantum mechanics concept, then explain that to the mathematician. The mathematician will write a mathematical model and translate into gate. As a computer software engineer, you will build the gates. This is the pure interdisciplinary task. You cannot find a one single man or single one man army in building the quantum solutions. Each quantum solutions will need minimum 4 people: domain subject matter expert, a physicist researcher, a mathematician, and software engineer. Now you can feel a sigh of relief. Oh my God, I need not to learn all these concepts. But you to understand what others are talking, you have to study all these concepts, physics and mathematics. That level is sufficient. So if there are any mathematician in this FDP, you have to go deeper. Similarly, if there is a physicist in this FDP, you have to go deeper. But most of them who are software engineers or computer science background, you can focus on programming, but you have to understand the mathematics and physics also. Make sense? Any question here? Okay. If no question, I will continue.
Hello, sir. Hello,
Yes,
sir.
madam. Yes, madam.
What about electronics and communication engineers? They should concentrate on physics, mathematics.
For electronics and communication, I strongly recommend go to hardware. You see, madam,
Okay.
domain. You will fall under hardware domain, where you
Okay.
can build control system, measurement system. See, that is where the lot of electronics devices and knowledge of electronics engineer required.
Okay.
So you can focus on hardware, madam. For example, as of now, there is no any common universal hardware for quantum circuits. You see
Okay.
here, all are sophisticated,
Okay.
and the quantum computers non-universal, meaning that IBM system control systems cannot be used for Google. That is why quantum computers are very costly. But as an
Okay.
electronics engineer, you can learn little bit physics, or else
Okay.
obviously when you join a company who are building quantum computer, they must have physicists already.
Okay.
You have to understand what they are talking. That level is sufficient, madam. But as a ECE professional, I recommend focus on quantum hardware. There are a lot of
Okay.
demand for hardware.
Okay.
Yes, madam.
And also, I have exposure to artificial intelligence and machine learning. That will also be useful in that field, sir.
At some point of time, if you want to optimize your circuit, for example, you are building a circuit, classical
Yeah.
circuit or quantum
Yeah.
circuit, you want to optimize it.
Yeah.
So for circuit optimization, there are many machine learning models. What you can do,
Okay.
you can build a corresponding quantum machine learning model. You can
Okay.
encode your classical circuit into a suitable quantum encoding system, then pass to that
Okay.
QML model that will give you the optimized output. Based on the output,
Okay.
you can redesign. But this part is already matured in the classical world. But still,
Okay.
if your control system has million parameters,
Yeah.
classical cannot handle. So in
Yeah.
classical, what we are doing, they are divide and conquer or map and reduce approach they are using.
Okay.
And with the number of qubits more, you can build. Actually, there is a company called Classic. They are
Okay.
exactly working on the field what you are referring, madam.
Okay.
The spelling is CLASSI.
Okay.
This organization. Search for their
Okay.
organization. They have exactly your problem. They are focused on
Okay.
this.
Okay. Thank you.
Okay. My pleasure. So anyone please ask question because the question and answer is more valuable compared to the topic what I have prepared. Any other questions?
Participants, please ask questions if you have any.
Okay. If no more
Hello.
question, let me continue. Yes, madam.
Sir, one
Can
more
we
question.
Yes, madam.
have to build the circuits based on the applications only, or the circuit will be general for all types of problems?
As of now, the industry is not matured enough, madam. So we are building separate circuit for separate problem. There are few common
Each
algorithms. What, madam?
okay.
There are few
For
common
every problem,
algorithms.
circuit will be different one. Is this like that?
Yes, madam. You see, madam, these are all basic algorithm, madam. You are seeing my screen, right?
Yes, sir. Yes.
So out of these things, the Fourier transform, phase estimation, super dense coding, these are all common. And
Common. Yeah.
Grover algorithm also nowadays become a common algorithm. But these
Okay.
are all applications or algorithm for applications. These
Yeah.
things, see, for example, you can use QAOA for any optimization algorithm, provided that optimization requirement is aligning with QAOA working model. That is where physicist will come and then explain you your your industry problem. A physicist will explain whether QAOA can be used.
Okay.
And as of now, because I am building multiple algorithms for various use cases, I don't find a common plug and play module, madam. There are many attempts. For example, there are many algorithms built by other organizations, but still we found they are either built for IBM Qiskit, mostly IBM Qiskit, or if they are common, they won't give a performance. Connecting to the real QPU is very difficult. So we have to use them as a patch, find the circuit, redesign the circuit in the respective QPUs. So in my observation, I have not seen a common circuit models or generic circuit for all problems. Indeed, that is where the industry is looking for researchers like you, particularly researchers from academy, because industry people don't have that level of patience and then spending time on research. We are good at implementing solutions, but when it
Yeah.
comes to research,
Some R&D is necessary after the
yes, madam.
executing, and is there any optimization solution? By looking all these things, we can change the construction.
Yes, madam. That is where actually I am seeing lot of industry revolution, but quantum is one thing where the industry and the institution get much closer because industry needs institution help now, meaning that industry needs academia help now. Um, Fortunately, we have been seeing lot of revolution, right? We are fortunate. The recent generation people, they don't know even TV and all, but we are from AM radio to FM radio, right? We have seen lot of
Yes, yes,
technology, but quantum is the
yes,
one
yes.
technology where I am seeing industry is really helping, really need help from academia.
Okay, okay. I got,
Right.
sir. Thank you.
Okay, madam. Any other question? Okay, let us move on to the next topic. So this is what is quantum inspired algorithm. Is inspired by quantum principles but run on a classical hardware. Solve complex optimization problem. Only optimization and computational problem. And leverage principle like superposition and tunneling. Useful for AI and optimization. And so these are all the reason why we need, because quantum computers are not available now. So we need to use quantum inspired algorithms. Now these are all the ideas given by this quantum inspired algorithm. These are all we covered already. Now I am going to demonstrate three quantum. This is the movie I was referring to, Transcendence. Okay. Now I am going to demonstrate three quantum inspired algorithms. So those are all very simple program, but conceptually very strong. So try to pay attention to each and every line of the code. I'm going to demo mode. I will share the updated PPT with Prabhati madam. Madam will share with you. Now we go to command prompt. Yeah. I'm running these things in Visual Studio Code. For many reasons, I recommend all of you to use Visual Studio Code rather than Jupyter Notebook. Yeah, this is my folder. You can see here I have three problems. One is quantum inspired dictionary algorithm. So this is also in Jupyter Lab. Okay, no problem. I'll run in Visual Studio Code. No problem. Here you see I'm not importing any packages, Qiskit or any other quantum packages. I'm importing only NumPy. I have written four uh, four functions. One is initialize population. See, when I say evolutionary algorithm, I am assuming that all of you know what is evolutionary algorithm. Can I assume that way? Okay, I'm assuming that way. If you don't know evolutionary algorithm, I will give you 1 minute for you to chat GPT or Google or Perplexity, whatever your preferred tool. Understand what is evolutionary algorithm. Evolutionary algorithm. And they are all part of something called meta heuristic algorithms. Either you can search for evolutionary algorithm or meta heuristic. That will give you an idea what is these algorithms. And here we are initializing the population with the random numbers. Fitness function, that is the challenge comes in fitness function, depending on your statement of problem, you can define your fitness function. Here in this algorithm, I'm not defining anything. I'm leaving it as a blank, which means it will depending on, because next time I'm doing random, so it will continue because um, then I'm building a classical algorithm for quantum rotation. Remember, in quantum inspired, we can use quantum superposition and entanglement and tunneling. So within those behaviors, I'm using rotation. Rotation is possible. So because that falls under within the superposition one. So I am using the quantum rotation by passing the individual and then best individual with the parameter theta. So that is possible to the new individual is calculated as simple calculation here with the difference plus difference times delta. So difference between current individual and then best individual. So whatever individual you have passed and what is the best individual in the population. And based on that difference times, we are calculating new individual. Then here is the quantum inspired evolutionary algorithm. It is repeating for the number of generation. For each generation, it is performing the quantum rotation, and that will populate a list of all population. From the population, we are creating the best one by finding the fitness. So since fitness is empty, it will find out the max value. But if you write some other fitness function, it will, based on that fitness function, it will find out the best one. So the fitness function is a scoring system. So it will change each problem statement. That is the reason I have not coded that one. Now we are adding the parameters, or we are initializing the parameters, and the 5 dimension 100 generation with the 20 population. The parameter is 10%. 0.1. Okay. Now let me run. So that let me remove clear up. So now output here. Let me run this one. Run this one. Okay. Anyone? No. I have two Python in my system. No problem. Okay, right. So I'm NumPy is not there. Okay, let me change my Python. So not exist Python. Mm. Actually, I will run in a separate setup. Considering the larger audience, I am doing this way. Okay. Okay, right. Now it is going to run. Yes. Kernel connector. Mm. Yeah, you get the environment prepared. And as I told you, I used to run on a Linux system. Now I don't want to confuse you. That is why I'm not running on Windows. My Windows system is not ready. Yeah, now it is ready. Now you can see here. You see the output is very fast. But if you do the something similar to this in quantum, you have to wait. The reason is that your job has to go to IBM server or cloud server where it will be put onto a queue, then it will be executed, then returned back. The latency will be there. Even though the execution time is very less, but the latency in job queuing, execution, after execution, post processing, and then sending, that will take time in quantum solutions. But in classical, since it is your local HPC, the outputs are very fast. That's what you are experiencing now. And this algorithm can be customized to meet your requirement. Also, the quantum rotation, if you want entirely new types of rotation, you can build your own rotation also, depending on the physical system what you are building. That is why you will realize we need help from this domain expert. So domain expert, you cannot decide what kind of rotation we can use, what kind of fitness function you use. Those things you cannot decide. That's why I gave importance to domain first. Computer programming, you see the flow, domain, physics, mathematics, after that only computer programming, because computer programming is the implementation leg. But ideation to design and modeling is all from domain, physics, and mathematician. So that is the reason why, uh, because in this one, even though program looks simple, but how to define the fitness function, how to define the quantum notation, that needs mathematics. How the mathematician will decide? He or she has to understand the physical behavior. That some expert has to explain. Is it clear? Any question here? I would like to stop here. If any question, I will answer.
Sir, one question.
Yes, madam.
As you told, when we can find the solution using classical computers, why we go for uh, quantum computers, as you discussed earlier?
Okay. There are multiple reasons, madam. One is
Yeah,
the problem what you are solving using classical, is it falls under exponential or factorial complexity?
yeah,
If it is
like,
falls under exponential complexity,
yeah,
the classical system cannot scale. For example, your solution will work for few 100,000 rows. If you
okay,
increase even 100 rows, the module what you have built will take double the time,
okay,
and you cannot increase more. It will not scale up, madam. Exponential problems are
mm,
optimized for small input.
okay,
We cannot increase them for the real problem. For example, I will tell you one use case, the AI
yeah,
and ML problem. Remember, I
yeah,
told you I am a data scientist. So
yeah,
this happened in 2017. That time,
yeah,
uh, the integration of big data and Python programming and web application are in the peak of that time. That time we
yeah,
built one solution, principal component analysis. The data
oh,
set had 100 million rows, sorry,
yeah,
1 billion rows, 100 columns. So the
yes, sir,
PCA module used to take 2 hours 50 minutes for 100 columns.
Okay.
When we increased one column, 101 column, the same model for 1 million rows took 6 hours.
Okay.
When I add one more column, 102, it went to 12 hours.
Okay.
Yeah, so that model what I built is suitable for less than 100 columns.
Okay.
But the real problem will have 1,000 parameters.
Okay. In that case, we have to go for
Quantum.
actual quantum computer.
Exactly, madam. So the scaling part is the reason why we need quantum.
Okay.
There is
Okay,
one problem. The
Yes,
weather
sir.
forecasting, that is the natural, the property of natural, right? Or the
Yeah.
property of nature. In weather forecasting, what are we dealing? Property
Yeah.
of nature. So
Yeah.
how the property of nature is captured? Using some sensing device. And
Yes, sir.
sensing device will convert your nature of property into binary number, right?
Yes, sir.
When it is converting like this, there is some approximation is happening, correct?
Yes, sir.
Due to the approximation, we are losing accuracy.
Yes, sir.
So we are feeding the approximator to your classical system. Even though your classical system is very powerful, but
Yeah.
there is a garbage in. That's why garbage out. That is one
Okay.
reason none of the weather forecasting system are accurate beyond 7 days.
Okay.
But in quantum, if you have the
Yeah.
proper quantum sensing device,
Yeah.
which can sense the property of nature and
Yeah.
feed without any approximation to quantum, the
Yeah.
quantum computer will process the most accurate information.
Okay.
That is imaginable.
Yeah.
That will give you good accuracy. That is the reason why Government of India National Quantum Mission has 4 verticals: quantum computing, quantum sensing, quantum communication, quantum materials.
Okay.
So quantum sensing falls under this vertical
Okay, sir.
because we need sensing devices.
Okay.
Yeah, these are all the 2 reasons why we need quantum computing.
Okay. Got it, sir.
There is a follow-up answer also.
Okay, sir.
Okay, this is acceptable, but how quantum inspired solution is able to run it on a classical, right?
Okay. Yeah.
Because in the algorithm, if there is any interference part, we will remove
Okay.
them
Okay.
and reformulate them using a different operation, mathematical operation. So here also you can see here in the quantum rotation. See, I'm just using a classical operation here, right? Individual, just arithmetic. But real problem is not arithmetic operation. I will use some rotation, entanglement, and based on the entanglement, some interferences like ancilla qubit, which is phase kickbacking. Those kind of algorithms I will use. That we cannot implement here. What I can do, the maximum I can use a superposition, rotate Rx, Ry, something like that, rotate, then use the data for some other linear algebra operation in classical world.
Okay.
Yeah, that is why these systems are able to run on a classical system.
Okay.
Very good.
Okay.
Any other
Okay, sir.
question?
Got.
Any other question? Because this quantum inspired solution is one of the highly demanded course, at least in my corporate network. Because they want to know how quantum inspired can be used for immediate implementation. Right. If no more question, let us move on to next one. Next program is quantum inspired genetic algorithm. Genetic algorithm also the futurist, what is called meta heuristic. So you already that one. So I'm here also. Same way, but here there are two operations, over and mutate. See, in evolutionary algorithm, there is only one fitness function with the quantum rotations. But in algorithm, there is a operation called crossover and mutate. It's a typical genetic, how the genetic is happening. Any race or any animal or any organism. So here also you can see here only numpy is used, no any other quantum. And here the crossover is a random number based concatenation only, nothing else. In mutate, we are doing just a comparison. Again, I wanted to keep this very simple. Then the quantum inspired genetic algorithm, I will initialize the population, then best individual equal to, I am finding the max of given population. Then for generation, the generation actually I wrongly used generation. I'm not using inside because that is not required inside anywhere. So new population, each time it is performing crossover, then at the end it will mutate. After crossover, for new population it will mutate for child 1. For child 2 also it will mutate. Based on that one, at the end, the maximum value will give the based on the fitness function. I think overall you got idea of where the fitness function is, what is this crossover and mutate. But here all are as for simplicity, I put as a classical operation, and these are all the crossover and mutate. We can put quantum. Now you may have a question: why there is a classical operation is compatible or which is easy to understand, which is possible? Why should we go to quantum inspired algorithm? So first thing I would like to uh, think about why we need nature inspired optimization model. The optimization is there is a strong mathematical model, right? Because it is a part of operation research. Optimization is the one of the mathematical branch where there are numerous algorithms are there. Then why mathematicians started exploring nature inspired optimization? Because some of the optimization are not suitable for smaller memory. That is when they decided to explore where we can achieve the same optimization with the smaller memory and less resources, because the human brain has lot of memory, unlimited processing capability. So we can optimize any model, but a computer cannot do that one. So that's why they looking for various optimization algorithms. One of the optimization algorithm is nature inspired. Through the nature inspired, they found out evolution algorithm, genetic algorithm, particle swarm optimization, ant colony. Those kind of things are falls under this meta heuristic. Now, think about this way. This is a natural behavior. And when we build a classical algorithm, that natural behavior is formulated into a Boolean algebra based model. Because Boolean algebra only computer can do. But nature is not binary. It is a complex number. Even you can remember what Richard Feynman told. You cannot simulate nature with binary. You need quantum mechanics. So it is much easier to replicate the natural behavior using quantum mechanics rather than a binary based computing, classical computing device. That is one reason why we are exploring this one. And since we don't have the capacity available, we are compromising with whatever possible in quantum running on a classical system as a quantum inspired. Those who are working on quantum inspired algorithm, including me, we are waiting. for a 40,000 qubit or 1 lakh qubit. Till the time, we will work on quantum inspired algorithm and file patent, keep accumulating intelligent properties in our name. Once the real quantum computer comes, we will convert these things into a quantum algorithm. That time it will be much easier to convert because only we have to change the interference or other natively parallelism based operations to a quantum operation. That portion we know already because this is we build the solution. We will plug that
But
into
what
this.
about the efficiency, sir?
Sorry, madam.
What about the efficiency? We are ultimately working on the classical computers only. Only functioning we are adopting, that is the inspired one, right?
Yes, madam.
So will it be the efficient
It is
like
um,
quantum?
see, it is not as efficient as quantum, but it is much efficient than the classical counterpart. If
Functioning
you
quantum, right,
yeah,
sir?
yes, madam. If you benchmark against a classical genetic algorithm and quantum inspired genetic algorithm will outperform.
Yeah, 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 yeah.
Yes, madam. Unfortunately, you have to run this on a QIO or Toshiba SQBM or Fujitsu digital annealer. You got it right?
Yes, sir. Yes, I got.
You cannot run on your own HPC. That's a good question because that's why Microsoft is charging 2 lakhs per month for their QIO. 2 lakhs dollar, not INR. Now you realize it is really business is there, big business is there, madam. This one, I
Yes.
remember I told you Azure Quantum QIO and SQBIM is charging $248 per hour. Yeah, I think per hour, something like that. Fujitsu is on demand. But anyone want to work on Fujitsu? Ask me. I will connect you with the Fujitsu people. I have the connection there in the research. Fujitsu research. Indeed, they are interested if you have a use case. For academicians, they can have go with the collaboration and then build something. Okay, right.
Sir,
Let us
may I
continue.
get your mail ID?
My email ID, madam.
Yeah, yeah.
I will type here, madam. Please
Okay,
note
sir.
it down.
Thank you.
Sir, I will share, sir.
Okay, madam. This is my contact details. Connect with you with the LinkedIn. I will connect you with the network. Okay, right. So now coming back to our quantum inspired genetic algorithm, let me run this one. All these programs I built exclusively for explanation, the classes like this, because I cannot go deeper because mostly these are 1.5 hour, 2 hour session, and FDPs are filled with a lot of topics, right? So that's why I keep the concepts as very simple. So in this one, the 5th generation is the best one. There are 50 generation. Out of the 50 generation, 5th generation is the best one. Sorry, it is the dimension, 6th dimension. Okay, right. Next, quantum particle swarm optimization. Particle swarm optimization is simple. It is not like mutation or crossover. It is
Sir,
simply yes, madam.
sir, there is one more question, sir.
Yes, madam.
I posted in your WhatsApp also.
Oh,
How
okay.
Fortune 500 companies take help of quantum computing? Will it be obsolete?
there are many organizations, Fortune 500, who are exploring quantum computing for their various research. I have to show another slide from another PPT. It's not part of your syllabus or your PPT. I will show now. So there are, yeah, this one. It will help you to understand. You see this image, what I'm showing, this image, you see in the leftmost user, you can see Merck, Airbus, BMW, JP Morgan, Wells Fargo, and AstraZeneca, Denso, Johnson Electric, Volkswagen. Like this, there are many organizations. If you see, they are diversified, not on one thing. So many Fortune 500 companies are exploring quantum computing. Why? Because they have a higher order differential equation problem which classical system cannot solve. So here the problem will not become obsolete, right? The problem is always going to stay, the use case. If you are running a defense business, yeah, defense is a business for the defense ministry. And if you are managing the very large logistics or supply chain network, or you are working on a pharmaceutical industry building drugs, and if you are in the financial marketing, you have problems which classical system cannot solve. So those problems, even whether quantum computer is there or not, they are going to stay. So quantum computing will not obsolete. Quantum computing will be there. But I think your question is whether classical system will become obsolete. And that also will not happen. You remember, it is always CPU plus QPU, quantum processing unit plus classical processing unit. And you might have seen the even algorithm, even the encoding I mentioned about classical. All our data are available as a classical system now. And display, those things are output device, input device, those are all classical systems. Suddenly, we cannot make the classical system obsolete. And it is not necessary also. Quantum computers will become computing superpower or powerhouse. So only the computation will be given to quantum computer. Remaining part, communication, database, comparison, validating, security, all those things, classical system will take care. Am I making sense? Hope that answered the question. Classical system will not become obsolete.
Yes, so thank you.
Quantum computer never replace classical system. I will show you one thing. You see this one, classical computing, quantum computing. There are much more going to come. Neuromorphic, optical, DNA, exascale, wearable, implantable. These are all still in the research stage. None of the computing going to replace classical system because all these computing are special purpose. Make sense? And I am part of Boson QSI. We are the first company will start exploring all computing. We already started exploring neuromorphic because our problems are finite element analysis and computational fluid dynamics. We are working on design optimization, volume optimization, topology optimization for mechanical problems for advanced level automotive industry. So for us, even if we give 120 core HPC is not sufficient for us. 120 core is the highest HPC core you can get it. Even that is not sufficient for us. Hope you understand what I'm telling, right?
Yes, sir.
Classical system, we think the reason is that we never exposed to that kind of problems. You know the problem called airfoil. I will just take a digress now because that will help you to understand airfoil, airfoil images. You see this image. This is the airfoil of any. You see, this is the various flight. You see here, the first flight airfoil is something different. And if you are able to change the airfoil, you can control the speed of your aeroplane. But the airfoil calculations falls under computational fluid dynamics. And for that, basic algorithm is Navier-Stokes. And Navier-Stokes formula is higher order differential equation. Now you understood, right, what kind of problem I am referring. This is not normal problem what we discuss in everyday life. This is the Navier-Stokes equation. You see here, it is higher order differential equation. Total derivative equal to pressure gradient, body force, diffusion terms. The formula looks simple, but if you put into airfoil for a flight or airfoil for or hydrofoil for a boat, a classical system cannot solve. And similarly, I would like to show another formula, Black-Scholes method. Black-Scholes formula. This is a financial formula. You see here, this is also higher order equation. You will wonder where are these formulas so far? We never read those things. Yes, of course. These are all research level problems. Even in commerce or economics, the researcher will come across these problems. If you see the terms, they are all looks very similar, right? But when you implement that one, the sigma and the you see e power minus r time tk and k phi. If you see the quantum equations, you remember psi ket equal to alpha 0 ket plus beta e power I theta 1 ket. Like this, many formulas you can find straight similarity between quantum mechanics formula and then physical formula, physical problem formula. That is the connection. That's why I keep on telling that learn mathematics. Okay. In the interest of time, let us run the QIPSO. Because usually I'm very energetic. I can go for a lot of questions, but today I'm not feeling well. The QAPSO, just a personal best combination. I'm just copying, but I can do any other operation. Then apply along axis. I am doing the fitness function. Then finding the best one. And I know that you all know what is particle swarm optimization. It is how birds are flying, the flock of birds, how they are flying. That is the particle swarm optimization. How they are deciding the leader bird. How optimized. See, if you see the birds are, it looks like a random arrangement of birds. It is not. See this image. You can see it like this. How they are, and then they are keep on moving, and the leader bird is the beginning. That will receive more stress compared to others, and particularly birds in the middle, they won't feel any pressure at all. So later, after some time, the birds in the middle, they will come to the leader place. Then the leader place will come to this place. Like that, this bird will move. That is the particle swarm optimization. Okay, these are all really very interesting part. How nature is optimizing everything. There is a slime optimization. You will surprise to see. how slime is finding their bread. Yeah, that's all from my side. Feel free to connect with me in LinkedIn or WhatsApp or email. I will connect you with the right people. I have the good network of professionals working in this field. I will help you to find out a good research team to publish paper or work on a research project if you have the skills. Over to you, Prabhat madam. Thank you.
Yes, thank you so much for very interactive and as well hands-on sessions.
Thank
It
you,
was
madam.
really helpful for most of the participants, and most of them were started asking for the recorded sessions as well.
Good, madam. Thanks, madam.
Thank you so much, sir.
Radha.
Participants, if you have any questions, you can please ask to the sir. I have shared his email ID as well. If you want, I think I have shared this number also. I shared the feedback form. Kindly fill the feedback form. Thank you all. We shall meet in the tomorrow session. Thank you, sir. முடிச்சு. நாளைக்கு என்ன பண்ற? நான் அங்கேயே இருந்துச்சா? உங்க அக்காவே வந்துருவாங்க. நீயும் busy இருப்பாங்க.
அதுக்குன்னு இங்க ரோட்ல பண்ணுவீங்க கோவப்படுத்த நாளைக்கு வர மாலை சரி நாளைக்கு நைட்ரா நைட்டு 10 மணிக்கு வருவாங்க அதுவும் நைட் 10 வர பாத்துக்க யாரும் வெள்ளி சனி ஞாயிறு അപ്പോൾ നീ